We've eagerly anticipated this moment as physicists for more than a century. Since 1916, this marks the beginning of a new era, an achievement offering a glimpse into one of the world's most fascinating and mysterious phenomena: black holes. Cosmic giants distinguished by their immense power, black holes remain extremely elusive. They are enormous in terms of gravitational influence, yet nearly hidden from our view, making them even more cryptic. One such black hole, potentially weighing between 2 to 4 million times the mass of our Sun, is the focus of this investigation. Over the past few decades, research on black holes has transformed our comprehension, taking us from a position of complete ignorance to one where we are beginning to observe them more intimately. The field of physics has never been more exciting. Michio Kaku has revealed that we have finally succeeded in peering into a black hole. This revelation opens up a wealth of new information that may provide insights into aspects of science we may have previously overlooked. Let us examine this thoroughly, diving into the realm of black holes and discovering what they contain. While the concept of space is vast and boundless, black holes generate numerous questions. Before we delve into the remarkable findings of Kaku, it is essential to understand the fundamental properties of black holes. People generally have a basic understanding of what black holes are, but there remain significant gaps in our knowledge. The theory of black holes dates back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes, though at the time, the idea was purely theoretical. It wasn't until about 50 years later, during the 1960s, that tangible proof of their existence began to emerge. Researchers studying the constellation Cygnus observed a blue star of unusual brightness releasing X-rays. This star was found not to be stationary but instead orbiting a massive black object. Upon further analysis, it became clear that these X-rays were being drawn into this object, leading to the term black hole. This discovery was a monumental turning point because it demonstrated that black holes were not simply an invention of Einstein's imagination, they were real, tangible entities existing in space. Scientists from around the world began focusing their research on a particular black hole in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years away from Earth. This black hole was about 14 times the mass of the Sun and exhibited extreme density, with a gravitational pull so strong that nothing could escape, not even light. This defining characteristic, its ability to trap light, sets a black hole apart. The idea of a black hole is both incredibly intriguing and terrifying. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. Any object that ventures too close is sucked in, and once it crosses a critical threshold, it is lost forever. This inherent risk is why it is so critical to expand our understanding of black holes. Following the discovery of Cygnus X1, researchers began an exhaustive search for other black holes. Now, estimates suggest that there may be over 100 million black holes scattered throughout the Milky Way galaxy. However, because of their nature, these cosmic giants are exceedingly difficult to detect, meaning we don't have a precise count. What is clear, though, is that there could be millions of black holes in our galaxy, highlighting their importance in cosmic research. The primary concern surrounding black holes revolves around their immense gravitational force. Anything that approaches too closely is gradually stretched to an extreme degree until it becomes a singularity. Simply put, black holes function like cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most alarming aspects of black hole research is that if a person were to fall into one, they would be stretched into an elongated form due to the extreme tidal forces. This process, known as spaghettification, would be gradual, and the person would perish long before reaching the final phase. In short, it is best to avoid falling into a black hole at all costs. Even though the nearest black hole is located some 500 light-years away, this still raises questions about the potential threats they pose. In 2021, a significant milestone was achieved when scientists successfully captured the first clear image of a black hole. This specific black hole was located in the galaxy M87. The research team took multiple images over several nights, stitching them together to create a comprehensive photograph that revealed shocking information. A black hole is more than just a massive void of nothingness, as many might think. In fact, a black hole consists of 3 distinct layers. 1. The event horizon, the boundary beyond which nothing can escape. Once an object crosses this threshold, it is inevitably drawn into the black hole. 2. The photon sphere, a region where light itself can be trapped in orbit. Any light entering this area is ensnared by the black hole's gravitational force. 3. The singularity, the core of the black hole, where all matter is crushed down to an infinitesimally small point. Here, the laws of physics as we know them break down entirely, making it impossible to predict what might happen. What is even more intriguing and troubling is that no two black holes are identical. While they all adhere to this three-layer structure, the way they operate can vary significantly. Normally, scientists observe celestial objects through telescopes. However, when it comes to black holes, this method is not practical because black holes cannot be seen directly. Instead, scientists must study them indirectly by observing the radiation and surrounding gas and dust they release. Sending probes like Voyager to explore a black hole is out of the question. Anything that crosses the event horizon would be drawn into the singularity and obliterated. Therefore, despite their three-dimensional nature, scientists must study these extraordinary objects through a two-dimensional lens. One theory regarding black hole formation suggests that they result from collapsing stars. When a star exhausts its nuclear fuel, it can no longer generate the energy needed to counteract gravity, leading to an inward collapse that may eventually create a singularity. To further investigate the nature of black holes, NASA researchers turned their attention to the core of the M87 galaxy. Here, astronomers observed a massive whirlpool of hydrogen gas spinning at phenomenal speeds of 1.2 million miles per hour. The force of the gas should have caused it to disperse, yet it remained intact. Scientists hypothesized that a colossal mass, weighing between 2 to 3 billion times the mass of the Sun, was holding it together. This mass could only be explained by the presence of a black hole. However, black holes may not only be formed by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating black hole. Kerr's solution demonstrated that rather than collapsing into a single point, a rotating black hole would form a thin disk, a phenomenon known as the ergosphere. This is a region near the black hole where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical tunnel could connect two distinct regions of spacetime, or, in some theories, even two parallel universes. If one were to enter a black hole, instead of being crushed, they might traverse this wormhole and emerge in a different universe or even a different time period. To comprehend how a wormhole functions, we must first understand the concept of space and time. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass warp this fabric, creating gravitational fields that cause other objects to move toward them. Imagine spacetime as a sheet of paper. If you mark 2 points and draw a line between them, that line represents the conventional path an object takes. However, if you were to fold the paper, you would create a shortcut, similar to how a wormhole might connect two distant points in spacetime. The possibility of wormholes and time travel. The idea of wormholes remains purely theoretical, but it has captivated scientists and science fiction enthusiasts alike. If wormholes do exist, they could serve as shortcuts through the universe, allowing faster-than-light travel between distant points in space. Some theories even suggest that wormholes could connect different time periods, raising the possibility of time travel. However, several challenges make wormholes an unlikely method for interstellar travel. First, a wormhole would require an exotic form of matter with negative energy density to keep it open. Without this, the immense gravitational forces of a black hole would cause the wormhole to collapse almost instantly. Second, even if a stable wormhole could exist, its entrance might be located inside a black hole, making it impossible to access without being crushed by the singularity. Despite these challenges, the concept of wormholes has inspired physicists to explore new frontiers in theoretical physics, including quantum mechanics and general relativity. Some researchers believe that quantum fluctuations in spacetime could create microscopic wormholes, though these would be too small for human travel. Black holes and the fate of information. One of the biggest mysteries surrounding black holes is what happens to information that falls into them. According to classical physics, anything that crosses the event horizon is lost forever. However, this idea conflicts with quantum mechanics, which states that information cannot be destroyed. This paradox, known as the black hole information paradox, has puzzled physicists for decades. In 1974, Stephen Hawking proposed that black holes slowly evaporate over time by emitting Hawking radiation, a theoretical form of radiation produced by quantum effects near the event horizon. If a black hole eventually evaporates, what happens to the information trapped inside it? Some theories suggest that information might be encoded in the Hawking radiation itself, while others propose that it could be stored on the event horizon in a holographic form. This idea led to the development of the holographic principle, which suggests that the entire universe might function like a hologram, with all information about three-dimensional objects encoded on a two-dimensional surface. The role of black holes in the universe. Despite their mysterious nature, black holes play a crucial role in shaping galaxies and the universe as a whole. Supermassive black holes, which can be millions or even billions of times the mass of the Sun, are believed to exist at the centers of most galaxies, including the Milky Way. These colossal black holes influence the formation of stars, regulate the movement of matter, and may even be responsible for the powerful jets of energy observed in active galactic nuclei, AGN. Observations of Sagittarius A*, the supermassive black hole at the center of our galaxy, have provided valuable insights into the behavior of black holes and their interaction with surrounding matter. Using advanced telescopes such as the Event Horizon Telescope, EHT, scientists have been able to capture detailed images of the plasma swirling around the event horizon, offering unprecedented evidence of Einstein's predictions in action. The future of black hole research. As technology advances, our ability to study black holes will continue to improve. Future space missions, such as NASA's LISA, Laser Interferometer Space Antenna, will allow scientists to detect gravitational waves from merging black holes with even greater precision. Meanwhile, developments in quantum physics may eventually provide a deeper understanding of the fundamental nature of spacetime and the connections between black holes, wormholes, and the universe itself. The study of black holes is far from complete. Each discovery raises new questions, challenging our understanding of gravity, space, and time. While black holes were once thought to be mere mathematical curiosities, they are now at the forefront of modern physics, pushing the boundaries of human knowledge. As we continue our journey to unlock the mysteries of the cosmos, black holes remain one of the most fascinating and enigmatic phenomena in the universe, offering not just scientific intrigue, but the potential to reshape our perception of reality itself. They are a direct reference to science fiction. However, the prediction of general relativity, no one has yet observed one, and their inherent instability likely causes them to collapse almost immediately. The potential for wormholes that can be used as routes of travel across space and time has captivated physicists for decades. While the concept of traversing vast distances instantaneously or traveling through time is undeniably exciting, the challenges are formidable. According to Einstein's special theory of relativity, nothing can travel faster than the speed of light, which places an absolute limit on the feasibility of wormhole travel, at least with our current understanding of physics. In recent years, a particular type of wormhole known as the CERN wormhole, following Royer's capture, has captured a lot of people's imagination. This hypothetical wormhole would link two remote points in spacetime, potentially even connecting different universes. Critics, on the other hand, argue that the CERN wormhole may be unstable or impractical due to extreme radiation and quantum-level forces. According to some physicists, the equations Einstein used to describe wormholes and black holes do not account for the quantum forces that govern subatomic particles. For a complete comprehension, a fresh theory that unites quantum mechanics with general relativity is needed. Such a theory, known as a theory of everything, could explain how the universe works at every scale, from the tiniest of particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. One promising candidate is superstring theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is viewed as a concerto, with different particles corresponding to variations in these strings' vibrations. Superstring theory also provides potential explanations for black holes, wormholes, and other cosmic phenomena by demonstrating how strings influence the fabric of spacetime. Despite its potential, superstring theory remains highly speculative, as it requires extra dimensions of spacetime that we cannot yet directly observe. These extra dimensions could be so tiny that they are effectively invisible to us. Some theorists suggest that these dimensions were more prominent at the start of the universe, during the Big Bang, but collapsed as the universe cooled and expanded. Theories that could help explain black holes, wormholes, and the very fabric of the universe remain some of the most exciting frontiers in contemporary physics. As we continue delving deeper into the mysteries of spacetime, black holes, and the cosmos itself, there's no doubt that there is much more to learn, and perhaps even more to discover, about the very nature of reality. As we approach the brink of groundbreaking discoveries, one key realization remains. We are merely getting started in understanding the true nature of black holes. Michio Kaku's contributions to the field of string theory and quantum gravity have only begun to offer insights. Despite technological advances such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our reach. The frontier of theoretical physics, specifically in the context of spacetime and black holes, is still an incredibly active area of research, filled with speculation and exploration. In addition to their role in shaping the fabric of spacetime, black holes have become crucial to discussions about the origin of the universe. String theory suggests that the collision of universes could lead to the formation of new ones, and black holes may play an important role in this process. This theory raises the possibility that our universe itself could have emerged from a collision between two pre-existing universes, or even that we might be living inside a black hole. Such a concept would dramatically alter our understanding of the cosmos. If this notion holds true, it could challenge everything we think we know about the Big Bang. It might even lead us to view black holes not just as destructive forces, but as potential creators, gateways to other realms or parallel universes. While the idea that black holes could enable interuniversal travel or even time travel is fascinating, it remains purely speculative. The internal workings of wormholes and the feasibility of navigating them remain profound mysteries. Even if wormholes are stable enough to form, the high levels of radiation and extreme forces surrounding them may make them inaccessible. Some physicists propose that, if we were able to stabilize a wormhole, it might theoretically allow travel through time or between distant points in the cosmos, but that remains a distant dream, at least with our current technology and understanding. Furthermore, when we examine black holes through the lens of quantum mechanics, we encounter even more fascinating questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales, and physics itself seems to break down when we consider objects like black holes. This discrepancy between quantum mechanics and general relativity has been one of the greatest challenges in theoretical physics. Theories such as superstring theory offer a potential framework for reconciling these differences by incorporating extra dimensions and providing new insights into the nature of gravity. However, this theory has yet to be experimentally verified, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unite quantum mechanics and general relativity into a single, unified theory, one that could explain the full range of physical phenomena, from the tiniest subatomic particles to the vastest cosmic structures. A theory of everything would not only deepen our understanding of black holes and other exotic objects, but could also reveal fundamental truths about spacetime itself. The idea that multiple dimensions, as predicted by string theory, exist beyond our perception may help explain the hidden forces governing the universe. It suggests that what we perceive as a four-dimensional reality may be just a small fragment of a much larger and more intricate structure.